So here is, I pointed out many times that vector spaces are very important in all these fields. They all have vector spaces, and a good way to think about all these different big data problems is points in spaces. So we can think of documents and queries as vectors in a high-dimensional space, where each word is a dimension, and then the component of the points of this incidence vector, which we defined earlier, which is just the number of times the word occurs in that particular document. And then relevance is measured by something like this, the angle between the query and the document. So here we have two documents, here we have the query, and we're interested in, for a given query, we're interested in documents which have a small angle, which are with respect to the query. And this will depend exactly how we normalize all these documents, because these, I said the coefficients were the number of times the word occurs, but they're actually not that. They tend to be normalized, and we discussed that later on. We had a similar discussion of going from points to vectors into distances for the recommender systems. There it was even trickier because we had these undefined components. So this sort of is obviously related to the way libraries have always been done. When you go to a library, similar books are next to each other. Children's books are next to children's books, and encyclopedias are next to other encyclopedias, and so on. And so this is just a notion of distance. When the query is encyclopedia, you go to the library, which has part of the library has encyclopedias. So it's placing yourself near the vector space here. The vector space is mapped from this very high-dimensional bag of words into a shelf of a library. So this idea of proximity is a very old idea and doesn't require any fancy mathematical spaces. So the vector space model is extremely old, 35, 40 years old. And we have a lot of dimensions. Remember, these big data problems are characterized by high dimensional spaces. And we have 500,000 or so dimensions in our space. And as we said here, the simplest choice is the incidence vector, but probabilities and things can give us and fuzziness can give us a different definition. So here we go back to the original non-fuzzy definition, and here we have our documents sitting in the space, and here we just have the space of China instead, because we have documents that only have 2 words in them, and here we have 3 documents. We've discussed the importance of general vector spaces in a lot of these optimization problems because it gives us a very broad approach which is intuitively understandable. We noted that the most important part of spaces is actually the distance metric defined on the space. These are not always metric spaces, because they don't have the distances which have these properties here, which are the standard properties of spaces, metric spaces. Typically, we do define distance so that it's positive, or 0 or positive. Often, distances are only 0 if x and y are the same, although sometimes distances can be 0 even if the points are different. That just depends on how precise the distance measure is. Typically, they're symmetric, because if they're not symmetric, we will just average them and replace d of x and y by half of d of x and y plus d of y of x. If you go, say, to genomics, both of these criteria are actually slightly violated, but not by enough to make a serious problem. And then we have the triangle inequality, and that's often violated. Triangle inequalities are a remarkable feature of Euclidean distances, which says that the length of any one side of a triangle is less than or equal to the sum of the other 2 lengths, obvious geometrically, but It is not true for general distance measures, and it is not typically important. So when we have a space, we can define a distance on that space, and then we typically look for everything within a certain distance of a document to see which matches it. That was absolutely the heart of all the work we did on recommender systems. The difference here is recommender systems weren't Euclidean spaces. In this case, you could use Euclidean spaces because we have real vectors with real components for the proper numbers for the components of the vectors. So this definition here, the standard Euclidean definition of a distance, is a perfectly reasonable distance definition. So usually 1 minus distance is what's counts, so that's the similarity. So the similarity being 1 means the distance is 0. So usually it says 1 minus d, or maybe 1 minus d over 1 minus d max, which makes that they're 0 when they're maximally dissimilar. Cosine similarity is one particular choice. It's the scalar product divided by the lengths of the vectors. So this diagram just shows a cosine similarity. Here's the similarity of 0.71. It says that all points on this line that have that similarity, and of course there'll be another one out here which had the same. We should only talk about which would have the same similarity. And you would look for points in this area here. When this says you're ignoring the length of a document by looking at cosine, and that is usually a good thing to do, but we'll come back and discuss that a bit later on. So this is just, again, the mathematics of calculating the cosine similarity. Take the dot product and divide by the lengths. Very straightforward. And because we divide by the lengths, if you have a short distance between the points, then they have a high cosine similarity. But if you have a high cosine similarity, the distance could be quite big because it could be divided, because these could be long documents, dividing by the length.